Recording is on, right?
Okay, I think we should be set. Can you hear that now? Okay. Okay. Bill, go ahead.
Good afternoon, everyone. My name is Bill Wells, coordinator for this class. We have the honor of having William Harrison to present today. I will call him Bill from here forward. Some of the metals, materials, and minerals most critical to today's advanced technologies are rare and often extracted from politically unstable areas of the globe. Bill Harrison will describe efforts to search for the identity potential sources for these critical materials within Michigan. This effort includes geological surface exploration, plus examination from samples of more than 500,000 linear feet of existing Michigan drill cores. Bill Harrison is Professor Emeritus and Director of the Michigan Basin Core Research Laboratory at Western Michigan University. And the Michigan Basin Core Research Laboratory is part of the Michigan Geological Repository for Research and Education. He has a BA and MA from the University of South Florida and a PhD from the University of Cincinnati. So take it away, Bill.
The only other thing I'll let you know is that if you stand on the podium, we'll be sure to capture you. You have about maybe a couple feet on each side.
Okay, how's that look? Thank you. Well, it's great to be here. Bill Wells and I have been communicating back and forth for almost 2 years now, so we were finally able to make this happen, and I think hopefully you'll find this an interesting discussion. At the Michigan Geological Survey down in Kalamazoo, we do a lot of studies about geology in the state of Michigan. We're focused primarily on the state of Michigan, and we're trying to understand all of the geological resources, the natural resources that exist in the state, because that's an enormous economic driver. And we'll talk a little bit more about the history of that in a couple minutes, but I would just want you to know that the Michigan Geological Survey is the oldest state agency that exists. The state of Michigan became a state in 1836, and the survey was enacted by an act of Michigan legislature in 1837. It was the first state agency to be created, and I think the real reason was that that new state didn't have much in the way of income, and so they were looking for natural resources and the development of industries in the state. And so along with agriculture and timber and a few other things that we know about, the minerals industry was one of the first industries in the state of Michigan. So Bill mentioned that we've been studying something called critical minerals, and I just wanted to give you guys a little bit of an idea of what critical minerals are. Sometimes they're also called strategic minerals. These are minerals that are absolutely essential for all kinds of technological activities and commerce and economic development in our society. And it's especially true in the United States, and you may have been hearing things in recent years and weeks about supply chain issues, and minerals have been one of those items that has been a huge global issue in the supply chain. There are a few countries that control a lot of these minerals, and they've been using it from time to time in political ways. These minerals, they serve a really essential function in the manufacturing of all kinds of products. And even if we just looked around the room, I could probably name 2 or 3 dozen different minerals that make up the different objects in this room. So it's something that we're really familiar with every day, but perhaps we don't think about what the origin of those materials really is. So hopefully I can give you a little bit of an idea here. This is just a list of a few of them. There's 15 elements and commodities on this list, and the only one that's not really considered critical is copper. The United States still does have quite a bit of mining activity in copper. Nothing really in Michigan that much anymore, although Michigan did lead the nation for decades in copper production. But all of these others, in fact, are found in these objects pictured on the screen. So if you have a cell phone or a computer or any kind of new technology, it's going to be filled with these different kinds of elements. This list is probably too small for you to see and read, but if you just look at the numbers in the columns on the left and the right, those represent the percentages of that particular substance that we have to import. And as you can see in my little summary box there on the upper right, there's 35 on this list. Of the 35, 13 of them were 100% dependent on foreign sources for those products. And a lot of those are absolutely critical in all different kinds of manufacturing activities. Also, another 25 are at least 75% imported. So as we can see that we're really tied into a global economy when it comes to minerals, and there's a big concern on that because of various unstable political circumstances that exist around the world. So I mentioned the Michigan Geological Survey, and that's an entity that now is housed at Western Michigan University, and we are responsible for trying to understand anything there is to know about the geology in the state of Michigan. The national point of view from the geology of the nation is done by what is called the U.S. Geological Survey. And the United States Geological Survey has been around for 150 years also. They started a program about 3 years ago. In 2018, this new program started to go out and look around the country, and each state took a component of that, and in their state they've been looking around for what opportunities there might be for various kinds of mineral information. And so we're involved in that, and we represent the state of Michigan in that project. Again, more technical details, but one of the key things that as geologists we try to do is understand what's going on in the earth and what is below our feet in a sense. And that's our job, because normally on an everyday basis you can't see what's there unless you go to some place like the Grand Canyon, and then you can see a mile down inside the earth. But for most places, in Michigan particularly in this regard, we can't really see much about the rocks that are underneath our feet here. So there's a lot of different techniques that we use, and in this particular program, we're using something called a mineral systems approach. And what a mineral system is really just a composite sort of three-dimensional view of the interior of the earth and what kinds of processes have gone on there and how the rock formations are deposited and how they occur where they do. These are just a couple of cartoons that I got out of some published literature. The one on the left is just schematic showing that somewhere deep in the earth there's a source of minerals, and those get moved around probably through volcanic activity for the most part, and they get moved up toward the crust of the earth. And then in the crust there are processes that separate those minerals, cause them to clump together or to link with some other kinds of minerals, and then eventually they form a deposit over there somewhere near where that star is. That whole process and pathway could take tens of millions of years, hundreds of millions of years. We don't really know all the timing on how this process works, but we do know a little bit about what's going on down in the crust based on decades, particularly the last 5 or 6 decades of being able to understand what's deep within the earth. And that's been developed through the use of deep boreholes, drilling, and also using a technique called seismic, which is sending vibrations or shock waves down into the earth and then measuring those reflections back. And you can interpret some things about the materials down there by doing that. So the 4 panels on the right-hand side are just schematic representations of different kinds of geologic settings or conditions within the earth. Some of those represent ocean basins. As you can see, the second one down is really part of an ocean, and the two continents on either side. In other ones, like the two bottom ones, you're looking more at regions near mountains. So this scale, the horizontal scale is thousands of miles, and the vertical scale is probably tens of miles. So this is a big view of what's going on in the interior of the Earth. And then you can see those various blobs and marked areas represent places where we know or we suspect that mineral deposits can form, and those would be places then you'd want to go and explore if you were looking for these kinds of deposits. So let's move a little closer to home and think about what's going on in the state of Michigan. As you're probably aware, if you walk around much or even have seen the surface of Michigan in any detail, that the surface of Michigan is mostly covered by sand and gravel. And that's a remnant of the last ice age when there were glaciers here in Michigan that were sometimes up to a mile or maybe even 2 miles in thickness. And as that ice melted over time, and it finally melted away from this area around 10 to 15,000 years ago, all of the rocks that had been picked up by those ice sheets as they traveled from somewhere up in Canada down to here, and they were also scouring out the basins where the Great Lakes now occur. That's why we have the Great Lakes where they are, because those were soft areas in the crust of the Earth that got dug out a little bit by those big ice sheets that came down from Canada. As that ice melted back, it left debris. And so most of the material on the surface of Michigan, at least in the lower peninsula, is this sand and gravel and sometimes some clay that's left over from the last ice age. The photograph in the lower right is a picture of a gravel pit. It's up by the town of Petoskey, and there's a lot of those. Every county has a few of those kinds of gravel pits, so they're all over the place, and they represent whatever this shallow covering of glacial material is, and it varies in places around the state. There's different kinds of rocks in it and different sizes and particles and so forth, but in general, it's loose debris that's been picked up by the ice and then left behind when the ice melted. What we really want to know, if we're really looking for minerals, there are some mineral debris in those glacial deposits, but what we really want to find are the solid rock deposits in what we call the bedrock, which would be underneath all that. And so you have to do drilling, and that's just an example in the middle of a oil and gas drilling rig, and Michigan's had a lot of oil and gas wells. Over 50,000 oil and gas wells have been drilled since the beginning of the 20th century. And as those wells get drilled, we have the opportunity to look at the rock material that drill bit goes through. Sometimes we can actually collect, if we use a certain kind of bit that looks more like a hole saw with diamonds in it, it can grind away some of the rock and then leave a cylinder of the rock, and we call that a core. And so we have lots of those in our collections at the university, and you can see in the picture on the left, that's our facility, and it's a big warehouse. It's like going into a Costco or something, except it's all full of rocks. That's all you can buy there. And then the little panel picture in the middle is some examples of some of these cores. So they're cylinders of rock, and they represent whatever that drill bit drilled through as it was going down. So we have rock materials all the way from the surface, and we actually even have a technique where we can collect the sand and gravel. It isn't solid like a rock, but if we put a plastic liner inside the bag, then we can actually collect that, even that loose, unconsolidated material, all the way down to around 17,000 feet. So in excess of 3.5 miles. So these drills have really explored what's going on down there, and there's probably more than 100,000 of those kinds of wells if you count all the different kinds of wells that have been drilled in Michigan. So that's a resource that we have to understand what's going on down below our feet. If we remove all of that loose sand and gravel that was left here by the glaciers, and we get down to the bedrock material, then we can actually tell what kinds of rock layers are down there. And the image on the left is the official bedrock geologic map of the state of Michigan, and those different colors represent different kinds of rocks. And the pattern is kind of interesting. It forms this bullseye-shaped pattern over the center of the state. The reason is because those layers of rock are actually not flat everywhere. they form in a kind of a depressed bowl-like structure. And the diagram on the right shows a slice through that. If you started up in the Upper Peninsula and just drew a line straight down toward Detroit, and cut that open, that's what you would see. And the total thickness of that at the deepest point would be about 17,000 feet. So it's a huge, thick pile of these layers of different kinds of rocks. And with all the drill holes that go down through there, we have quite a bit of knowledge about what's down there. And some of those images in the right-hand side, there's one of those cylinders of rock. That's a piece of salt that was drilled. And then some of the products, actually, that salt can be mined out and produced as different kinds of products. And then some of the solid rock minerals that come out of the bedrock as well. So you may or may not know that Michigan, because of this early initiation of the Michigan Geological Survey, we understood quite a bit about the rocks in Michigan very early in the game. And in fact, the first commercial mines in Michigan occurred just a few years after Michigan became a state. Up in the Keweenaw Peninsula, copper was discovered up there. Actually, it had been mined by the Native Americans for probably hundreds of years, picking up pieces on the ground and digging shallow pits. But eventually we got into some pretty serious underground mining and tunneling and so forth. And then also in the area around Marquette and a couple of other places in the UP, iron ore was also discovered and mined back in the before the Civil War, actually, in the middle 1800s. So Michigan really has a long history of mining and looking at the rock and geologic deposits to try to understand what's down there. We normally think of mining minerals as metallics, and that's what most of those minerals on that critical mineral list are. Not all of them, but vast majority of them are different kinds of metallics. And so the properties that metals have make them very important and useful in aspects of technology. Just to kind of reiterate where some of the activity is, the copper mining areas were primarily mostly in the Keweenaw area and a little bit in the very far western part of the Upper Peninsula. There is a new mine near Marquette called the Eagle Mine, and they're actually mining copper there as well, but they also mine nickel and they mine PGE, which is platinum group elements. So platinum, palladium, and a few other kinds of very nice precious metals. And then there's a few other projects people are exploring up there, and there's something called the Back 40, which is down in Menominee County, almost to the Wisconsin border. And that's a project that's in the works right now. It's being permitted, and probably in the next couple of years there'll be some mining development there as well. And it actually is a very rich deposit in zinc. And zinc is a critical mineral. It's in a lot of dietary supplements, but it's also a real common element to put into alloys, all different kinds of metallic alloys. And then the iron mining, and not only did they get a lot of iron out of there, and Michigan led the nation for probably almost 100 years in iron ore production in the area around Marquette, and then there's a couple of other areas down by Crystal Falls and all in the far western part of the Upper Peninsula also. If you ever tour around up there and you happen to be in the little town of Ishpeming, which is on US 41 about 15 miles west of Marquette, there's a big hill on the south side of this little town. It's called Jasper Knob, and it stands out. If you just look across the horizon, you can see this for miles. It's about 400 feet above the surrounding areas. And if you climb up on top of that, this is the rock that you see. As I mentioned, in most of Michigan, the glacial deposits covered a lot of the bedrock, but in this part of the state, and particularly the western part of the Upper Peninsula, there wasn't that much glacial material. So a lot of times there's actually bare bedrock exposed. And this particular type of rock is called a banded iron formation. It's really old. It's about half the age of the Earth. The Earth's about 3.5 to 4 billion years old, and this rock's about 2.1 billion years old. So it's really old stuff. It formed early in the history of the North American continent, and these deposits have been around since that time. But in the 1840s and 50s, people actually started to figure out ways to mine it and then actually turn it into some usable material. The raw rock material isn't that usable. You've got to separate the iron parts out and then do some smelting to get the pure iron phase. But this is the primary source of iron everywhere in the world. Not just this layer, but the same layer is present all over the world. And if you go up on the Keweenaw, this is the Quincy mine on the left there, and that's still open for visitors and tourism. There hasn't been any copper mining since the 1970s up there. Other areas in the world have produced more and produce today. But in the Keweenaw Peninsula, all the mining was underground, so they had to have these shafts and these buildings that just look like some sort of crazy barn is actually covering the hoist that lowered people up and down into the shaft, down as deep as 9,000 feet below the ground. And they also used it to haul the ore back up to the surface. And then it was taken to the smelters and separated the copper out there. So it's an interesting place. You can go and see. They even have a little gift shop. You can buy some souvenir pieces of copper if you're interested. So this is sort of the western half of the Upper Peninsula. It's a map. And all of those brown and reddish areas are places where there's iron deposits, and the yellow is where all the copper deposits are. So you can see spread out in the little different areas. And when you look at the surrounding geology in those regions and use that mineral systems idea that I was talking about earlier, you can see that the geological conditions in the rocks below the surface there are different in those two different places. So it helps people understand why that deposit is where it is. And in fact, that big long yellow streak where all the copper mines are is a gigantic fault. Not too different than the fault in California, the San Andreas fault that everybody talks about all the time. But it's a billion-year-old fault, so it's not doing anything anymore. But the reason that it's important is that that fault acted as a conduit to move those fluids from deep in the earth up to near the surface and concentrate them along that area. So again, that mineral systems model showing how those fluids came from somewhere in the earth and then up to the surface, they happen to come along that big fault there. The little green arrow is over by Marquette, and that's this newest mining operation. It started in 2014, and it's the only nickel mine in the United States, or actually in North America today. So it's a pretty unique situation. And it's estimated they've been producing now since 2014, and they'll probably produce for another 3 to 5 years. But it's estimated they'll produce about $10 billion worth of nickel out of this mine. It's a really nice deposit, and it's supplying this important mineral. Again, nickel is an alloy that is used in lots of metallic substances. Yes, ma'am.
Is it an open pit mine?
No, it's not. It's an underground mine. Today, it's very difficult to permit and get and manage open pit mines because of environmental impact. The interesting thing about this mine is it's really using 21st century technology. And essentially what they do is, as they mine the rock out, they stockpile it on the surface, and after they get a certain distance away from that mined face, they take all that rubble and mix it with cement and backfill all the tunnels. So everything is going back underground again. And the environmental conditions are really quite amazing. It's quite a pristine site. I actually have a photograph, an aerial photograph of the site in here to show you guys. Yes, Bill. Oh, I'm sorry. The question was, is this mining today going on in an open pit fashion? And I said, no, it's not. Open pit mines, there still are a number of those around the world, but they're messy and they create lots of environmental issues. So anytime you, this deposit is only maybe 500 or 1,000 feet below the surface. So that makes sense to do an underground mine in that case. These are just charts showing the production history. Let me go back to this one a little bit. This is for the iron ore, and you can see the graph, that orange line there started back in the 1840s, 1850s, and kind of got off to a slow start, but as technology evolved, the production ramped up quite a bit. And you can see on the left-hand axis, those are in metric tons, 10 million metric tons, 20 million metric tons. So there was a lot of iron ore being produced, particularly in the late 1800s through probably the 1960s or 70s. I also put on here just a few examples of some of the things that iron went for. So in the late 1800s, about 1890, 1895, the technology evolved to the point where we could build steel frame skyscrapers. So things like the Empire State Building, most of all the modern skyscrapers are all steel frame now rather than just stone or concrete. So the increased availability of iron to make steel made this jump in development and technology in construction. And then, of course, since we live here in Michigan, the automobile capital of the planet, as Ford and a number of other companies began to develop in the late 19-teens and 1920s, and the demand for metal was even higher, iron for steel in automobiles, Michigan supplied most of that as well. So really until I'd say about 1990 or so, Michigan was probably the leading iron producing state in the United States. This is the chart for copper, and again you can see the numbers aren't quite as big. Annual production is maybe a quarter to a fifth of what the iron ore was. But in terms of value to our industrial society, you can see that in the late 1800s, 1870s, 1890s, a lot of people found out they didn't have to use outhouses anymore. And when you do indoor plumbing, most of the pipes for indoor plumbing are made out of copper. Also, everybody takes electricity for granted. Electricity travels on copper wire. So between the plumbing, development of infrastructure, we hear about infrastructure today, the infrastructure back at the beginning of the 20th century was really for people's homes and businesses and buildings and things. So between bringing plumbing indoors and bringing electricity to these areas, Michigan copper really drove all of that as well. And you can see that the urban areas got electrified first, and then by the 30s or so, that moved into the rural areas of the country as well. Now there's very few places in the US at least that don't have electricity or indoor plumbing. Thank goodness. There are some interesting byproducts in mining these substances as well. In the copper mines, there's a fair percentage of silver mixed in with the copper. So as these hot fluids came up along the faults and from somewhere deep in the earth, a lot of different kinds of minerals were picked up. And so some of the trace elements, even some rare earth elements that we hear a lot about today, got picked up along. The primary mineral and the one that drove the economic development was something like copper or iron, but the subsidiary or secondary elements in there also provide value. And today, people are even going back into the dump piles and the spoils and the rock quality that wasn't viewed as being the highest quality for mining the primary metals and looking for these secondary metals. So I think there's some interesting opportunities even to go back into these old mining regions and find additional minerals. And in this case, silver was a very significant secondary component. So in terms of this research program that we've been involved in, it actually started in 2017 as a result of an executive order from President Trump. It became pretty obvious that a lot of these metals and these minerals that are super critical to our society and really to national defense too, a lot of the technology that our military uses is based on a lot of these different kinds of materials. So he issued an executive order that we get busy and go out there and try to figure out what's going on and see if we can find more of these minerals, to work on the supply chains to make sure those are solid, and even to look at recycling and looking back at the old waste piles. So there was a whole series of activities that were developed. And this, by 2018, the funding became available and projects were started. In the first year, they were mainly looking at rare earth elements. And as you saw from that list, quite a few of those components in cell phones are rare earth elements, and in all kinds of technology like computers and so forth. So we spent that first year looking around and seeing if there's some rare earth elements, and we actually found some old published reports that there are a few areas in the state of Michigan, mostly in the Upper Peninsula, that do have small amounts and trace amounts of these rare earth elements. So there's some possible potential there. In 2019, they issued a second research program, and there were 10 more elements in that, including things like aluminum and cobalt, lithium, to name a few, platinum. And the items that I've highlighted in yellow here are ones that we've been able to demonstrate have either been commercially produced in Michigan, or we know about deposits in Michigan that can produce them. So you can see, at least already in just the early stages of this program, we figured out that there are a few of these that are available here in Michigan. And we talked about the platinum group elements coming out of New Eagle Mine in near Marquette. And there's also a little bit of cobalt that gets produced out of that, along with the copper and the nickel and the platinum group stuff. There's a fair amount of cobalt. One of the key things that cobalt is really important for, you hear about lithium a lot in batteries, but lithium is the cathode, which is the positive charged component in a battery. You have a negative pole in a battery as well, and that's almost always cobalt or graphite. So we know that Michigan has deposits of both of those, and so in addition to perhaps finding some lithium, we already know that we can find graphite and cobalt, and battery technologies are going to be something that's really going to be big in the future. This past year, and really just wrapping up here now at the end of this year, will be the year 3 project, and you can see there's a whole variety of other things, including magnesium, which is a light metal, a very nice light metal. It's almost as light as aluminum, and it makes a great alloy as well. And manganese, these are both elements used very commonly in alloys. And then potash is not a metal. It's actually, it's a kind of a salt. Sodium chloride is normal table salt. Well, potash is actually calcium chloride. So the only difference is the cation in that crystalline salt form. In potash, it's potassium, and in regular salt, it's sodium. And in fact, if you ever see imitation salt or diabetic salt, that's a potassium chloride salt, because it's the sodium that causes people to have problems with their blood pressure. So we know, and actually for the last several years, I've been doing some personal research on potash, and there's a huge deposit of it here in Michigan that we could tap into. Excuse me. Oh, yeah, I brought some too, but I'll drink yours. It's probably better. So, just a little quick summary of what we've been doing here for the last 3 or 4 years. The very first thing was we had to spend a bunch of time figuring out what we already knew, in a sense. The way that science works is that a lot of people do a lot of different kinds of projects, and a lot of times that'll get published and put in a journal somewhere, or the information is stored in a library, but not everybody knows about it. So one of our first objectives was to compile as much basic information about the geology of minerals in the state of Michigan as we could. So that's where we came up with all of the ideas about the production history and where these minerals are formed and where they're found, and all the historic data that I've already shown you. So that took us almost a whole year just to get that stuff together. The second thing was to make a complete and detailed inventory of all the drill holes. And as I mentioned, there's probably over 100,000 of these drill holes out there. And so We have built big databases, and we're using Microsoft Excel as our database management software. And so we have these lists now of all the wells and where they're drilled, and it's all been sorted by county so that we know anywhere in the state what kinds of drill holes are present. Not all of those drill holes had any samples collected from them. So sometimes somebody drilled a well, but they didn't record anything, or if they did, it's been lost, so we couldn't find any records about that drill hole. But a lot of them did. And so we have this huge lab. We have over 500,000 feet of these core samples from all over the state of Michigan at our lab in Kalamazoo. There's another facility that's actually run by the state of Michigan up in the Upper Peninsula at the old Air Force Base there near the town of Marquette. So between the two collections, we have tens of thousands of drill holes with samples and well data, and that stuff can then be tested to see what kinds of potential mineral deposits there are in those. So building that database was really important as well. Another thing that we did was there are files, and companies, they go out of business after a while, and sometimes they actually will donate their company records to a public institution like a library, or in our case to our research lab. And also the core storage facility up in Marquette has huge collections of these records as well. Almost all of this stuff is old technology. It's all paper records, paper maps. There's very little digital information there. So another objective that we've had is to get all of that stuff in digital form. So it can be shared with anybody. You won't have to go to the spot and pull out the papers and look at them. These records are scanned and they're being put into digital archives right now. We're actually using a university system called ScholarWorks, which is where all the scholarly academic documents, including students' theses and dissertations and publications and works of art and stuff that faculty members do, get stored in a digital archive, and that's where we're storing a lot of these records as well. So they'll all be available to the public as time passes. And then the last thing was to make sure that we have good maps of where all of the old historic mines were and where there are potential sites and regional areas where the geology suggests there could be other potential mineral deposits. So that's actually what we've done for the last 3 years, and it represents tens of thousands or hundreds of thousands of individual records. So we haven't really done a lot of chemical experiments yet to look at new information. We're simply building a giant database of what we already knew, but we're getting it all into one place. So here's a map of the Upper Peninsula, just to give you some idea. There's about 20,000 little well spots on that map. It's a little hard to see because it's a small scale, but those represent all the drill holes up in the Upper Peninsula. And we have the data for all of those now in our records. Just a little close-up view of that western part, again, where the yellow strip is the old copper mining. The iron mining is actually down toward the central and bottom part of that map. And the 3 stars represent, or 4 stars represent, relatively new areas. The one in the right there near Marquette is the position of that Eagle mine. So actually, if you get up on a hill there by that Eagle mine, you can see Lake Superior. So they're about, I'd say, 8 or 10 miles from Lake Superior where that mine is. But it's all underground, so you don't really see much of anything on the surface. And then the other spots are the newer proposed mines that are being permitted right now. So here's a picture of the Eagle mine. And if you look in that top picture, just at the very horizon, you can see Lake Superior, just kind of off in the distance there. But basically, that's the entire surface area of the mine. The actual mine shaft itself goes down at an angle and goes out under that forested area in the back, but and it goes down a couple thousand feet. But the surface area is not really that big a footprint. It's about, I'd say about 50 or 60 acres, so it's not a huge area. It's actually part of a old volcanic system. It might be the neck or one of the branches off of the feeder conduits for an old volcanic system. But in that zone, there is a pretty high concentration of these metal elements. And as you can see there, about 3.5% of that total rock is nickel, which is really a rich concentration for an ore deposit. When you think about natural ores, even 1% is pretty high. So 3.5% of any particular metal is really quite extensively good. And the copper is almost 3%. Cobalt is pretty low, it's 1/100%, and then the platinum and palladium are in the order of parts per million. So you've got to mine a lot of that rock before you get very much platinum or palladium. So they are mining a lot of rock. They're mining about 750,000 tons a year. They've been doing that since 2014. What they do then on this site is they actually concentrate that rock and get rid of all the non-metallic material, and they crush it up and create a concentrate that is mostly either the nickel ore or the copper ore. And then those two are separated and shipped separately to a mill up in Canada, and it gets refined there, and they make pure nickel and pure copper deposits. And that's also where they separate the cobalt and the platinum and palladium at that processing facility up in Canada. So we've spent a lot of time talking about the Upper Peninsula, and that's historically where most of the mining occurred. But there's actually quite a lot of rock in the Southern Peninsula as well. And I showed you this map of the state before. It's a little different color pattern, but basically the same thing. And you may see around the edges, particularly around that ellipsoid of the gray layer, there's a bunch of little red splotches. Those are the only places where the natural bedrock actually occurs at the surface or close enough to the surface that you can see it or mine it. And that particular layer is the layer from a time in Earth history called the Carboniferous, which is where most of the coal deposits are in the whole world. It's about 250 to 300 million years ago, and the Earth was a tropical system at this time around Michigan, and we had lots of swamps and so forth that we got a lot of coal deposits. And so that layer in the area up in the Thumb area and down in the southern part near Jackson, Michigan, there was significant amounts of coal mining. From the late 1800s until about the 1950s, Michigan produced about 1 million tons of coal a year. None of those mines are active today, and coal, it comes from a lot of other places, but at least in historical times, Michigan did mine some of these different rock layers. In addition, as we've looked at the drill holes that go all over the state, and there's about 60,000 in the Lower Peninsula that we have data for, we found out that there's other kinds of layers even deeper in the earth. And as we've talked about before, there's some salt layers down there. There's actually an underground salt mine down by Detroit, and that's where most of the rock salt comes from that we use on the roads. But in the center part of the state, some of that salt is actually the potassium-bearing salts in addition to the sodium-bearing salts. And that potassium salt is really useful because the element potassium is an absolutely critical mineral for all life. And that's why you eat bananas, because you need to have a little potassium in your diet. You could eat potash salt, but that's kind of doesn't taste as good as bananas. But so we got to have potassium out there, and the farmers use it a lot. It's one of the key 3 ingredients in fertilizer is potash or potassium. So let me show you a little bit more about that. This is a diagram of that central part of the state now, with just the roads on it and the counties. And then that big brownish or orangish area is where we have found drill holes that go down deep enough and encounter this salt layer that has some of that potassium in it. Where the little green arrow is where there actually was a commercial mine. From about 1997 until 2013, one of the big potash producers in the world came out of Canada and discovered this deposit down there and drilled a bunch of wells and started mining it. It's pretty deep. It's about 7,000 feet down, so a mile and a half is pretty deep. But they drill a well, and then they pump fresh water down. It dissolves the salt. Then they pump that brine or that salty water back up to the surface and evaporate the water off, and then they get the crystalline salt back again. So it's kind of like making sea salt, but you're making it out of rocks instead of out of water in the ocean. And when
May I interrupt for just a moment?
Yes,
I have
please.
a question in the chat, and my curiosity is, are you accepting questions? Do you want them during
Yeah,
the...
sure, anytime.
Okay, because I don't want it
I've got the whole
time-
afternoon, so whatever you guys want to do.
Well, it came in a few minutes ago. I didn't want it to age too much.
No, that's fine.
Do these located drill mines include oil mines? Is your work locating abandoned mines or well sites that are leaking methane or other possibly hazardous gases?
The answer is yes, 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 and yes. And all of those wells that I mentioned, a proportion of those, probably about 40,000 or so of those, are oil and gas wells. Michigan has been drilling oil and gas wells actually since the 1880s. We don't regulate that stuff. We simply do the scientific studies. If you talk to the folks in Lansing at Eagle, they're the regulators of that stuff. I do, however, have access to all the records, and I know what has gone on in each of these wells. So for the most part, most of the wells either are still currently producing or they've been what they call plugged, which means they pour a bunch of cement or concrete down in the hole to seal it off. The issue about methane, and this has come up recently with some EPA regulations, most of the methane is not actually, that's leaking into the atmosphere, is not coming from the well itself. It's coming from the technology that we use to transfer that. It's natural gas. Methane is natural gas. And so once it is brought to the surface from a well, it goes into a series of pipelines, into treatment facilities, into all kinds of processing and so forth, and some of it even gets re-injected back down in the ground and stored to be used later on. So basically there is a national organization called PHMSA, which starts out with a PH and some other acronyms. They monitor what's going on with natural gas. And there is something called fugitive methane, and that's natural gas that mainly escapes from the infrastructure. There's a chance that a little bit can be leaking out of wells, but I would say predominantly most of that methane is coming from the various pipelines and processing plants and so forth. In terms of other substances, there are a few other components. Of course, crude oil, most of that is pretty well contained in the tanks and so forth, but there are instances of leaking tanks, and there actually, if you go to the DEQ's websites, you can find some information about where those sites have been in the past, and there's been a long history of cleanup. There's a division of DEQ called Remediation and Redevelopment, and those guys monitor all of the, I can't remember the name of the legislation, but there's an act in the state of Michigan that identifies these kinds of sites, and there's a lot of them all over the state, and there's an active list that you can actually look at and see where that stuff is. We don't actually do any of that regulatory monitoring. We just look at the geology part of things. But yeah, that's a good question, and there's some resources out there. If you want, you can contact me, and you can contact the HAS folks, and they can give you my email, and I can steer you towards some of that information. Does that help? Okay.
Yes, thank you.
Okay. Long-winded route around. So most of the work, in about 2008, we received a huge collection of these core cylinders from about 75 wells drilled all over the state of Michigan by this Canadian mineral company that was searching for the potash deposits in the state. And they gave all that stuff to us for scientific research, which was really cool. And we've been studying that stuff and and looking at the rocks and testing them and mapping their distribution and so on. What we found out is that this deposit in Michigan is actually kind of flying under the radar. Most of the production of potash in the United States comes out of New Mexico and Utah. The U.S. uses almost a little over 6 million tons of potash a year in fertilizer. And I'll show you a map in a second where all that is going on the ground. In 2017 is the latest statistics I could find. We only produced in the whole U.S. about 480,000 tons. So that's only 8% of the total domestic demand. That means that 92% of that particular product is being imported. Most of that actually comes out of Canada, but there is a fair amount that's coming from Russia as well. There aren't very many. There's only 9 countries in the whole world that have potash deposits. So it's a pretty limited commodity. There's an awful lot in Canada and Russia are the 2 biggest places in the world. But for us here in Michigan, it would be great if we could just get our fertilizer, our potash component of fertilizer right out of the ground here in Michigan. So let's think about that and see what we might be able to do. So here's what it looks like. It kind of looks just like that crushed rock salt. Those 2 little glass bottles there are from the Canadian source, and they've actually got a little bit of iron. That reddish tint on there is a little bit of iron mixed into the salt deposit. The stuff in Michigan is actually pure crystal clear. It looks just like the rock salt that you spread on your sidewalks or on the roads. But if you look at the map of the U.S., you can see that those bright colors, the oranges and yellows and reds, that's where the high demands are. And that's up to, 11.5 tons per square mile of application in the big high-intensity farming parts of the Corn Belt in Illinois and Indiana and Ohio and even southern Michigan. The little black squares with the red dot in the center are where the 3 mines are, one in Utah, one in New Mexico near the Texas border, and then the one up in Michigan, off of Lake Michigan, which has now been closed. That got closed in 2013. There is some interest in reopening that mine, but it hasn't happened yet. So the Canadian guys, their deposits are pretty shallow, and they can actually go underground and mine it in tunnels just like any other kind of underground mining. So it's pretty inexpensive. The Michigan stuff, the diagram on the upper right, it's an underground facility, but it's a well. It's too deep, 7,000 feet below the surface. It's too deep to dig a mine that deep, so they drill a well, or several wells in this case. They have a cluster of wells, and they inject water down the well. You can see that diagram on the bottom there. Water goes down on the left side of the well, circulates through that blue layer, which is the salt layer, dissolves some of the salt, and then that concentrated brine is pumped back to the surface, and then those 2 little dome-like areas, which are actually not that little, they're probably 300 or 400 feet across, are evaporating units. And inside there, they use natural gas to evaporate the water. The water is actually collected and condensed and reused again. So once the system gets going, they're recycling the water that they produce each time. One of them is for collecting the potash salt, and the other one is for collecting the sodium chloride salt. And they use that sodium chloride salt. It's good enough to be table grade salt, but they actually use it to make water softener salt. That's what water softener salt is. It's just sodium chloride, little cakes of sodium chloride salt. So we've mapped this geological formation. It's in a unit called the Salina A1 Salt Formation. It's pretty thick. It's up to 450 feet thick in different places in Michigan. It's pretty deep, 7,000 to 9,000 feet below the surface. It occurs in a large area in that central northern part of the state of Michigan We've actually found those deposits in wells throughout 17 different counties, but some of them are pretty thin layers and probably really not worth the effort to make a commercial mine out of it. But in about 8 counties, it looks like it could be. And there was a report a number of years ago that estimated that if they started mining this salt, it could be about a $65 billion asset for the state of Michigan. So this would be an enormous economic driver from a mining standpoint. Yes, sir.
If there's that much valuable material, why did they stop mining in 2013?
So the Canadians bought that mine so that they could test and see what Michigan had. The size of the deposit in Michigan and the depth makes it pretty expensive. And their mines up in Canada, as you saw, they just go underground with tractors and machines and stuff, and they can scrape it right up. So it's cheaper to produce. But then to get it back to Michigan again, it costs somewhere between $50 and $100 a ton just to ship it here. So the advantage of having it here probably overcomes that additional cost. They really didn't want anybody else to compete with them. So when they shut their mine down in 2013, they also destroyed that processing facility. So if anybody wants to come back in and do it again, they've got to build a whole new plant, which costs about $500 million. So that's the constraining factor right now, is capital investment. There have been a couple of companies expressing interest, and they've been to our lab, and we've worked with them and done testing on the samples, and it turns out that this Michigan potash salt is the richest grade of salt anywhere in the world. So it's 3 or 4% better than any of the Canadian stuff, but it's kind of expensive. So that's going to be the big deal. When this project first started back in 2008, potash fertilizer with the potash part of fertilizer was selling for about $1,200 a ton. Last year, it was only selling for $300 a ton because the Russians are just dumping huge quantities on the market right now. So even with the transport difference all the way from Russia, it's still cheaper to buy the imports than it is to. But if we get dependent on those imports, then we could be in trouble. That's the whole issue with all these minerals, is if somebody else is producing it, you don't really have control from your national security standpoint. So this is just a map. What those circular lines are depths, and the heavier lines are 500 feet deeper as you go toward the center of the state, and the deepest part of these layers is over there by Saginaw Bay. It's about 2,000 feet deep at the bottom and at the top at the edge of the state, and then it gets down to about 9,000 feet out in the center of the state. So it's pretty deep. Where the commercial mine is over there on the left. It's actually up near the town of Hersey, if you know where that is. Not too far away, actually. Over toward the center of the state a little bit. Yes, yes, Bill.
That's the reason Dow Chemical is in Midland, Michigan area.
That's right, because they're a company that extracts minerals from these salts. They didn't particularly come after potassium, but they got other things. They got magnesium, they got bromine. A lot of the chemicals that they used in their processes came out of the salt deposits, and that's why they're here in the state of Michigan, because of all these rich, mineral-rich salt brines. The salt water in these brines is just full of all kinds of minerals. Calcium, potassium, sodium, strontium, lots of good things. And there's still a little bit of commercial brine mining in the state. Over by Ludington, there's a Dow Chemical facility there that's still producing some brines, and a couple other places in the state as well. So these are pieces of some of those cores. When one of those exploration companies came to our lab, we did a bunch of testing, and what we did was we sliced the core up into little segments and sent it off for an analysis, and they got back the information about what the chemistry was. And then on a few other pieces, I actually used a Dremel drill and just ground off a continuous sample so they could actually get all the information up and down through the core. And we've got about almost 17,000 feet worth of these salt cores from 70 different wells. So we did a huge amount of testing, and we know the chemistry of this salt pretty well now. And it's got some great stuff in it. Here's a photograph of one of those cores. I held it up against the light so you could actually see through it. That's a 4-inch thick piece of rock. And that salt is so clear in places that it's almost transparent. The other interesting thing is that potassium has a radioactive isotope. Now, it's not dangerous like uranium. It's not that radioactive. But there's enough radioactivity in there that it does generate a few gamma rays. And this chart on the left is a graphic representation of a device that's lowered down into the well that has all these different sensors on it. And the sensor on the left that has all the wiggles in it is a gamma ray sensing tool. So you can actually explore down in your well with a remote device that senses gamma rays, like a little Geiger counter actually. And any of those areas where you have those big peak deflections on that graph show the layer of potassium-rich deposits. So, and the length of that deflection is proportional to the concentration of potassium in the rock. So we measured in the core, we get a number, we can estimate that then based on what these gamma ray logs are showing us, and we can map this. I've got a data set that has almost 4,000 wells in it now in the center of the state, and we can measure the percentage in each of those wells, and it varies as you move around the state. It turned out that when the Canadian guys set up that mine near Hersey, they picked one of the best areas, and they must have had some additional data as well, because that's some of the richest potassium deposits anywhere in the state. They only mined about 500 acres underground, though, so in that 16 years of mining, they didn't mine very much at all, considering this deposit's about almost 3 million acres throughout the whole state. So here's a little map of the center of the state, and that big cluster in the sort of left-hand side of the green box is where the commercial mining operation went on. It's just outside of the town of Hersey. And you can see there's a lot of wells all over the place. The ones with the big yellow circles, we actually have those core samples from. The other wells, we just have the gamma ray logs. But it's pretty easy to compare the two. And so once you get outside that yellow box, there's almost nothing in the way of that potash salt. You don't see anything on those gamma ray logs. Whereas inside that green box, you see a lot of it. So this is kind of the highly prospective area for the mining of this materials. It's going to take an enormous capital investment to make it happen, but it's certainly a resource that's there. And as geologists, that's the best we can do, is we can tell you what's there. You have to find some businessmen or some economics people to actually make it come true. So in terms of the Michigan potash, we're getting close to the end here now. There are two different layers in that salt. One's a little more concentrated than the other. One's about 50%, 55% potassium chloride, and the other one's about 44%. But when you look at other areas in the world, like in Canada, the concentration of the potash is only between 18 and 24%. The Utah stuff, that's where a lot of our, and New Mexico, where most of our domestic production is right now, 24%, less than 22%. And then the Russian stuff is in about the same range. So most of the world's potash deposits are in that range, from maybe 15 to 24, 25% of this potash mineral. The Michigan deposits are in the high 20s to low 30s, maybe even up close to 40%. So it is, as far as I can tell, the richest deposit of potash anywhere in the world. It's probably also the deepest and the hardest to get, so there are some concerns there. Well, just to kind of bring things back full circle, when Bill asked me to come and talk, I guess almost 2 years ago now, we had just started working on this project, so I didn't have a whole lot to say. Now, basically, we can say that we've spent the last 3 years gathering up as much data and knowledge as has happened in the last 150 years in the state of Michigan. We've got that all in one place now, and we understand what the mineral deposits are in the state, what has been historically produced, the quantities, the locations, and what resources we have to go out and keep hunting. There's no doubt that Michigan is a rich state in terms of mineral deposits. We've seen that throughout the state's history. It takes an effort to go out and figure out where these things are. With our modern technologies, our ability to build these giant databases and building on the work of the last 150 years of miners and geologists and academics that have been studying mineral deposits in the state of Michigan, we have a great resource now to evaluate, and I think we have significant potential opportunities for future development of mineral resources that will not only help the economy of the state of Michigan, but it's also great for the national interest of the United States to have access to these resources. Thank you all. Yes, sir.
Take one here and one on Zoom,
Okay.
back and forth, so. Yeah.
Yeah, because they won't be able to hear you online if you don't use the mic.
Won't go to the online.
Actually,
Oh.
even with the microphone, we can't hear you at home, but if you could kindly repeat the question, you're welcome to
Oh,
hand
okay,
your
I'll be
mic
happy
off.
to.
But if you just repeat the question or the comment, that would be fantastic.
That would be fine, thanks.
We've been hearing a lot lately about the upcoming potential shortages of the rare earths and lithium needed for the batteries that are going to be going into this exploding market for electric cars.
Absolutely.
What's your assessment of how much Michigan can contribute to perhaps, meeting that need?
So, just to give you some perspective, the mine that the Canadians built in 1997 was first discovered in about 1985. So it took them 12 years to get from the initial discovery and recognition of those deposits to actually having a producing commercial mine. I would say in general, the regulatory environment and the capital investment environment during the early 1990s was better than it is now. So my guess is that any new commercial development of mining operations is likely to take anywhere between 10 and 15 years to develop. So it would be great to think that we could turn the spigot on or turn the spigot off. But the fact of the matter is, this is a very complex kind of process. And in addition to finding and identifying these deposits, they have to be defined, and economic assessment has to be made of the quality and the capital investment needed to do it. And so the time frame is of a concern to me. To me, a much better opportunity is to look at recycling or somehow utilizing known and existing deposits and resources. So I mentioned early on that there are old mine dumps around. It would be a lot easier to go in and reprocess the materials out of those than it would be to build a whole new mine, because the processing facilities are already in existence. The Eagle Mine up near Marquette actually refitted an old iron mine processing facility called the Humboldt Mine in Humboldt, Michigan, about 30 miles away from the mine itself. So I think there's low-hanging fruit available to us. The other issue is that the big concern right now is that there are several countries in the world that control a number of these mineral deposits, including like Russia with the potash and China with critical minerals. China controls over 90% of all the rare earth elements being produced in the world today. So and other countries are recognizing this as well. Australia is starting to develop a very strong minerals mining program. So I think looking for alternative sources to some of these materials rather than maybe necessarily going with the cheapest one out of China could be a little bit of a short-term opportunity as well. But I think between recycling and reprocessing, that's the quickest low-hanging fruit on these things. To go to a new mine, and we've identified a number of places in the state of Michigan where there's potential for building new mines, but those are not short-term solutions. So that's probably, in practicality, that's probably the biggest concern I have about the mineral situation right now, that there aren't a lot of short-term fixes. Working on the supply chain to find some friends that have these resources that we can interact with is certainly going to help us. But I'm not hugely optimistic about it. I think it's going to be a problem for quite a while.
Susan, do you have any questions on Zoom?
I don't currently have anything. Thank you for asking. Oh, I do. One just came in. Does Michigan have any rare earth deposits that could be considered for development?
So there's a couple of places where we've seen analyses of a few samples that show there are rare earth elements present. And one is in the area actually surrounding that nickel mine up near Marquette. When they were exploring for that mine, they also drilled a bunch of wells out away from where the current mine is. And because those wells didn't show any nickel, they decided not to keep any of that core material, and they donated it to the state of Michigan. So we have access to all those core samples. Plus, they ran chemical analysis on all those samples. And I've studied that stuff, and there are various sort of small level concentrations, in some places some bigger concentrations of rare earth elements in those rock samples. So it would be a matter of developing a new mine, and that would fall under the issues I just mentioned, because from the time you discover a deposit, and now we know that those things exist out there, to actually having a commercial mine that's producing that stuff for us to use, we're talking probably a minimum of a decade. So there are resources out there, but there are no short-term solutions other than basically looking at recycling, working with the supply chain, and some reprocessing potential, I think. So yeah, there are new resources out there, but there's not a short-term choice there.
Do we have any questions here in the classroom?
Yes, sir.
Being an analytical chemist by training,
This stuff must sound beautiful.
I'm curious about what types of analytical techniques you'll use to analyze the core samples. I mean, you've actually analyzed the elemental analysis.
Yep.
And so forth.
So there's a whole bunch of different things we can do. There's a really rapid and short-term technology that's only become available recently, and that's a device called a handheld X-ray fluorescence unit. And we have one of those at our lab, and a lot of places have them now. They're actually kind of modeled after the Star Trek technology of phasers. They look like that. They're a little handheld plastic device. It shoots an electron beam. That beam is bounced off the solid particles in the rock, and then the information is collected back, and the electronic signal is then sent to a computer, and there's programs in there that process that information and identify the chemical elements based on how that electron beam affects the solid particles in there. So most of those devices we have can analyze all of the metals and most of the rare earth elements quite easily. It's difficult on some of the very lightest elements, like lithium. Most of those devices can't measure lithium, and it's tough on sodium and magnesium as well. But for a quick and easy thing, and we've done this with our core samples already, you can scan it, and you can scan it at any scale you want. We had one student that did 2 centimeter interval scans across about 1,000 feet of core. And it took him about 3 months to do all this, but that's tens of thousands of measurements But this is really quick and easy, and it's saved in digital form, and you can make graphs and everything, so you can see exactly where these concentrations of maybe up to 80 or 90 minerals or elements are. So that's really good. To be a little more precise, we would use something like ICP-MS or atomic absorption or some other benchtop technology that has a little higher precision, and there you would need to actually grind up a sample from your rock and then send it to a lab that is certified. And there are technical labs out there. The one we used for all the salt analyses was a lab up in Saskatchewan that does all of the analysis for all of the potash companies in Canada. So there are technologies out there, laboratory-based, but that handheld technology is pretty cool because you can do that on the fly and it's non-destructive. So that's kind of a nice way to approach it.
We have somebody who has a question. Suzanne, go ahead. You can unmute yourself.
Hello.
Hi.
I have a comment first. My father lost his father in a mine crash, or iron ore crash in the area of the Crystal Falls area when
Oh,
my
yeah.
dad was just 3. And
Well, I tell you, it's a dangerous profession. I mean, we
Yeah.
don't appreciate what those people have gone through, that's for sure.
right, it's true. And I have a question. What kind of things of nature produce such deposits in various places of different minerals and so forth? I mean, to have such large ones in some places and not others.
Yeah, so it depends on what the geology underground is. Like if you've got a fault down there, for example, a lot of the fluids, almost all of these mineral resources come from deep in the earth somewhere.
Okay,
Maybe down below the crust, down in the interior of the earth. And they get moved to the surface in various ways, but a lot of it is through volcanic activity. So in areas of ancient volcanism, and if you've ever gone up on the Keweenaw Peninsula where all that copper is, there's a very dark black rock there called basalt, which is a common volcanic lava. And it's just like the lava that's flowing out of volcanoes on Hawaii today. And so when these volcanoes move fluids from deep in the earth up toward the surface, it actually allows for those metals to get carried along with them. There are certain kinds of chemical conditions that need to exist, though. The pH and the temperature and pressure of the environment that they're passing through is meaningful. The kinds of the kinds of rock layers that the lava flows through is important, because a lot of times those lavas can pick up additional minerals out of the surrounding rocks. I mentioned that nickel deposit up near Marquette several times, and then the presence of rare earths in some of the surrounding rock formations. There's a dark greenish shale unit called the Michigami Formation up there west of Marquette, and it actually occurs around the shores of Lake Michigami up there. That rock is full of magnesium, and so as the lavas would pass through that, they could actually pick up some of the magnesium and concentrate that and make an ore deposit with some of that magnesium. So what happens in and around volcanoes and in any place deep underground where the temperature and pressure is high and there's fluids moving through the system, either molten rock or even water and gases, that's going to remobilize those mineral deposits, and then they flow into certain areas near the surface where we can actually get access to them.
thank you. Thank you.
Bet. Yes, ma'am.
Is core drilling and sampling allowed offshore in Michigan?
I think it depends on what it's for and what the target is. We don't have very many core samples from anywhere other than on land. However, when they built the Cook nuclear power plant, one of the things they had to do was demonstrate, because their water intake pipe went out about 3 miles offshore, they had to demonstrate what the layers were down below the surface of the lake bottom. And so we've got core samples from the shoreline all the way out to around 20,000 feet offshore because that was a regulatory issue that they had to do. There are no, in the United States, there are no drill holes of any kind of exploration for natural resources under the seabed of the Great Lakes. There are a couple of wells that start on land and then have been drilled down and turned on angle and drilled out under the lake bottom. But they are tens of thousands of feet down below the surface. There are no wells that start on the surface of anywhere in the lake bottom and go down. And there's only about 6 or 7 of those kinds of wells that start on land and then wind up out under the lake for their bottom hole. So yeah, no. The only way we know anything about what's underneath the lake water is by remote sensing techniques. So those seismic, when you send vibrations down into the ground, occasionally they've run boats up and down, and those things can send sound waves down, and that reflects back and shows us what the layers look like down below the mud on the lake bottom. But we don't have any actual samples of any of that stuff.
Susan, do you have another question on Zoom?
I do not currently, thank you.
I brought some business cards with me. If anybody has any questions about anything, we're a public facility down there in Kalamazoo. We're right off 131. If you happen to ever be in that area, you'd be welcome to come by and look at our materials, or if you have particular questions about anything, please feel free to contact me. We also have multiple web pages where you can go and look at resources of things we do. Another project that we've been heavily involved in the last, since 2005, is looking at carbon sequestration. And we've used all our data from all these deep wells around the state to look for places where we can actually inject carbon dioxide waste down into the underground environments here in the state of Michigan. So we've got a lot of information about that as well. Yes, sir.
You've mentioned you've got about 500,000 feet of core samples in your warehouse down there.
Yes.
Is there a requirement that when somebody they have to give you the core? Or
No, everything we've gotten has been generously donated to us. We get stuff from oil and gas companies, mineral exploration companies, even the Michigan Department of Transportation. Whenever they build a new bridge or a road or something, they drill a core to see what the substrate is like to make sure that it's going to be stable enough to hold the weight of bridges. When they built that new Detroit River bridge crossing that's going to go over to Canada, they cored, we have one core that's like 1,300 feet continuously all the way down through all the different layers to make sure that the substrate is stable enough, the bedrock is stable enough to hold the weight of that bridge. So yeah, we have cores from the footings of the Mackinac Bridge. So those are some out in the water too, but they were out on a barge and they were drilling down into the lake bottom under the Mackinac Bridge. That was back in the 1950s. So there's no requirement. The only requirement is that companies report what they found and provide a written document of all the information about where the location of the borehole is, what they saw all the way down, and any records that they recorded from it. So like those tracings of the gamma ray and things like that, they have to turn that stuff in. But as far as the samples go, that there's no specific requirement. We do have, that's about 2,500 wells, that 500,000 feet. It's from about 2,500 wells. So it's not a very big proportion of all the wells drilled. But we also have, sometimes they won't use a core, which is like a big hole saw. They'll just use a bit that grinds the rock up into little bitty chips. And we have those little chips. Sometimes they'll have a geologist on the site that actually collects those chips as it drills down. And then they package them up in envelopes or little bottles. And we have that from about 30,000 wells. So we do have a pretty large collection of material. Not all of it is the solid rock, but a lot of it's just the little chips that they drilled up when they were drilling the well. But it can tell you something about what the material is. You can analyze that with an XRF, for example, and find out what the minerals are in it, even those drill chips.
I'll use your microphone so everybody can hear in both locations. How many students have you worked with, and how many hours of slave labor, if I can use it, went into collecting all this data?
So, Bill, I started at Western Michigan University fresh out of my PhD at Cincinnati in 1973. And I retired from teaching in 2003, and I've been running this research facility ever since. Although I did start the research facility back in 1982. So it's been going for quite a while, longer than that. I've served on over 50 master's and PhD student thesis committees, and we typically have anywhere from 3 to 5 work-study students working in the lab at any one time, plus a few master's students. So yeah, we always say, I can't do all this stuff myself. I'm just getting far too old to do that. But the student help, all that scanning and digitizing that we talked about, that was all done by students. So we get these federal grants, and we'll get $30,000 or $40,000 to hire students to do all that scanning. So we've scanned, I'm guessing, several million pages of these documents over the years.
Thank you.
My pleasure.
Thank you so much. We appreciate it.
Well, I'm happy to do this. I did this, I ran a 3-day course. Western has a program called the Osher Lifelong Learning Institute, which is very similar, I think, to your HASP. And 3 or 4 years ago, they asked me to do a 3-day course, or 3-week course, 1 day each week.
Have a great day.
Geology of Michigan. So we went through everything. We looked at every layer and every fossil that ever existed in Michigan and everything. So it was, that was a fun thing to do too. So yeah, this is the kind of group I like to talk to, because they're not playing on their computer or talking to their girlfriend on the cell phone. So.
Ask you the question.
Yes, ma'am.
The Eagle Mine, because I was
Peter and Diana, I'm going to close the class. Have a great day.